Hello everyone, welcome to another Project Bytes Crash Course video. So today we'll be looking at normal distribution. So I'll go through some general normal distribution advice, followed by what is continuous random variables, and then normal distribution, which is actually a subset of continuous random variables. Then after that I'll follow up with some questions as well. And so some general advice is that whenever they ask you to calculate the probability of something directly above or below the median, because the median is literally the middle value, so usually the probability that anything is either above or below is always going to be half. And we always want to use less than or equal to or greater than or equal to when calculating probabilities in a normal distribution. And for any questions, they usually ask you to write some assumptions about normal distribution. So remember to write those down as well, whether it's central limit theorem, independence, or something else. So this is the content I'll go through. First will be continuous random variables, followed by normal distribution and some things about it. Then lastly, standard normal distribution, and then independent normal variables. So the first part is continuous random variables. So in the previous chapter, we talked about discrete random variables, which only takes a finite number. But the thing is that continuous random variables are values that are unpredictable. So this can be like finding the probability that something is the digits of pi. But because pi has so many digits down to however many figures, or like finding the exact height of someone like 171.12345678231, so on and so forth, it just keeps going. You cannot get a really specific number. So that's what a continuous random variable is. However, we can find a range of possible values that can be made. And so when we allow the sample size to increase to infinity, the graph distribution will usually approach a smooth curve, which is what makes a continuous random variable. So the properties of probability density functions in continuous random variables are as follows. So we let fx be the probability that x takes on a specific value. So if we integrate fx, we will get a certain probability, and this probability will always be greater than or equal to 0 for all real values of x. Then if we take the lower limit and upper limit as negative infinity and infinity respectively, if you take the entire area beneath that curve, it should be equal to 1. Then another thing is that the probability that a is less than x less than b equals the integral of fx, which equals the area under the curve of y equal fx bounded by x equal a and x equal b, which in other words means is the lower and upper limits of a and b respectively, and the probability that x lies within that region. Then the thing is that the probability that x equal a specifically will, or any constant for that matter, will always be equal to 0. So that's another thing to take note. Unlike discrete random variables where it can take on a specific number, in the continuous random variable, it will always be 0 for any specific number. So another thing is that the less than or equal to, greater than or equal to, all these signs are the same as with or without the equal to sign. The total area under the graph is 1, and if f has a maximum, then m is called the mode. And if the probability of m being less than or equal to x, it's only going to be equal to half, and this m is called the median. So this is one example of a CRV question. The lifespan x of a certain bulb is a continuous random variable with probability density given by fx equal 100 over x squared, for x is greater than or equal to 100 and 0 otherwise. So sketch the graph of f and determine whether f attains a maximum value. What is the probability that the bulb lasts more than 200 hours given that it's still functioning after 150 hours? So for the first part, just sketching the graph of y equal 100 over x squared, where x is only defined for more than 100, and so at x equal 100, it has reached its maximum value because from then onwards, the graph is continuously decreasing. And so also just remember to shade the black dot there to represent x equal 100. Then for part 2, you want to find the probability that the bulb will last more than 200 hours, given that it's still functioning after 150 hours. So first of all, we need to find the probability it lasts more than 150 first. So we're going to integrate our 100 over x squared with lower and upper limit 150 and infinity respectively, which should give you a 2 over 3. And to find that specific probability in part 3, we're going to find the scenario where both less than 200 and greater than 150 happens, and divide it by the probability greater than 150. So if you do that, it is going to be the probability of 150 less than x or less than 200 divided by 2 over 3, which if you integrate the x power minus 2, it will become power minus x, and then you do that, insert the upper limit, lower limit, you eventually get a probability of 1 over 4. So the next part is cumulative distribution function. So given a continuous random variable x with period f, The cumulative distribution function CDF of x, written as capital F, is defined as a probability that x is less than or equal to a specific value of x. In other words, the integral of ft, where the lower and upper limit is minus infinity and x respectively. So you can see that if you want to find the f, it's basically this entire area up until a. Yeah. So previously on probability density function, we wanted to find a specific range. But with cumulative distribution function, we are looking from negative infinity to a specific value. And because this cumulative distribution function is the sum of the area beneath the curve, as long as we keep increasing, the value of fx will always keep increasing also. So this is why if a is less than b, then fa will be less than or equal to fb. Then as we approach like negative infinity where there's little area, fx will probably, will have a limit of 0. And if we go to infinity, the limit of fx will be 1. So the range of fx is basically from 0 to 1. And if you want to find a specific range of the probability, it's just going to be fp minus fa. Then if we differentiate our fx, we will get fx also. And f is a continuous function. So now let's consider normal distribution and the situation where we have a large number of 1 kg bags of sugar, which are weighted to check how accurately they have been filled. And so usually the results will be shown in the histogram as you can see. So notice that the histogram is almost symmetrical about the mean, and the percentage of bags with weight close to the mean is higher than the percentage of bags with weight further away from the mean. And so what this means is that if a smooth curve is drawn through the top of the columns, this will give a distribution which is roughly bell-shaped. And this bell shape can be modeled by a normal distribution, whose probability density function is given by this very complicated expression, but you do not need to memorize it. Just know that this is called the normal distribution. So if a continuous random variable x follows a normal distribution, we can write it as x squiggly line normal of mu and sigma squared, where the mu is the mean or the expectation and the variance is sigma squared. So these are some normal distribution properties. So it will be symmetrical about the line x equal mu, where mu is the mean. The mean, median, mode are all equal to mu. And it approaches the x-axis as x approaches whether it's negative infinity or positive infinity. The total area under this curve is equal to 1. And so if we want to find the area under the graph, it gives the probability of a is less than or equal to x, less than or equal to b, which equals the area under the curve, where y equal fx represents the probability distribution function of the normal curve. So probability that a is less than x, where x is less than b, is given by the area under the graph from x equal a to x equal b. And this is some general things, you don't need to memorize it, but basically if you move like 1 standard deviation away, 2 standard deviation away, 3 standard deviation away, it's approximately, like if within 1 standard deviation, it's 68% of all the values. If you're looking at 2 standard deviations within the mean, it's about 95% of all values are accounted for. Then if you want to consider what lies within 3 standard deviations, positive or negative, you will see about 99% of the values drawn. And so the shape and basically the curvature of this normal curve is completely determined by the value of this mu and this sigma respectively. So like let's say on the left figure, x and y have the same standard deviation but different means. So because it has a greater mean, then y is forward. But on the right figure, they have the same mean, but let's say x has a greater standard deviation, the peak will not be as high and the values are like more distributed and more spread out. So that's for normal distribution. There's also this thing called standard normal distribution. So without the graphing calculator, to find probabilities with different means or standard deviations, we need to carry out a standardization so that the mean is 0 and the standard deviation is 1. So what happens is that we're gonna take our x minus mu divided by sigma, we get this random variable z, which has a normal distribution of mean 0 and standard deviation 1. So what happens is that if you want to find the probability that x is less than or equal to lower capital X, we're gonna minus mu divided by sigma on both sides. And what happens is that when we have the capital X minus mu divided by sigma, it becomes our z. So actually in the past, we used to refer to standard normal distribution table for calculation of probability involving standard normal random variable. Then for non-standard normal random variable, we perform standardization first before looking up a table in now MI26. But the thing is that now with the graphing calculator, Standardization is usually applied to solve problems where mu and or sigma is unknown. So these are some examples for standard normal distribution. So this function x has a mean of 1.6 and a variance of 4. But in other words, the standard deviation is square root of 4, which is 2. So by standardizing x, we want to find the probability that x is greater than 0, the probability that modulus of x is greater than 2, probability that 0 is less than x less than 2, and the value of k if modulus of x minus 1.6 greater than k is 0.63. So for the first part, we are going to take our 0 minus the mu divided by sigma. So 0 minus 1.6 over 4 square root will create our z. And with our z being normal or 0 and 1, we can press into the calculator and we'll get 0.788. Then for part 2, find the probability that the modulus of x is greater than 2. We want to find the probability that it's either less than minus 2 or greater than 2. So for the first part, minus 2 minus 1.6 divided by square root of 4 plus the probability that 2 minus 1.6 is great over 4 square root. Our z is greater than that. So we do that. We will get the two probabilities, which we sum together will be 0.457. Then for part 3, probability that 0 less than x less than 2, we are going to find the probability that if we standardize everything, we have a 0 minus 1.6 over 4 square root and a 2 minus 1.6 over 4 square root. If we simplify, put the actual number inside, you will get a 0.367. Then for part 4, what we want to do is that we are going to standardize this also. So we have our minus k and then less than equal to x minus 1.6 less than k. Then we standardize it. You'll get probability that minus k over 2 less than z less than k over 2 equals 0.63. We're going to inverse the norm in our GC and we'll get k over 2 equals 0.89647, which equal to 0.896. And then another example. So the diameter of copper wires found in a certain type of equipment may be assumed to have a normal distribution with mean mu mm and standard deviation sigma mm. We know that 99% of all wires produced have diameters exceeding 2.24 mm and 5% of diameters exceeding 2.30 mm. So we want to find the value of mu and sigma. So we're going to let x be the diameter of a randomly chosen copper wire in mm, and then let x have bound distribution of mu and variance of sigma squared. So given that px greater than 2.24 is equal to 0.99, we're going to standardize it. So our 2.24 minus mu over sigma equals 0.99. So from our GC, we're going to inverse norm the 0.99. And so what happens is that we're going to get 2.24 minus mu over sigma is equal to 2.3263. So and then we bring up our sigma. That's the first equation. 2.24 minus mu equal minus 2.3263 mu sigma. Then given that px greater than 2.3 is 0.05, we're going to find the probability where x minus mu over sigma is greater than 2.3 minus mu over sigma equals 0.05. So using GC also, we're going to find the inverse norm, which will lead us to get our 1.6448. That gives us our second equation. So if you put both of them into the GC using simultaneous equations, you'll end up getting a sigma or 0.0151 and mu equal to 2.28. So that's how we try to find these unknowns. We basically do standardization and we'll get two equations. And with these two equations, we put into the GC and then we see what the values are. So yeah, that's how we solve these unknowns. Then we go on to properties of independent normal variables. So let's say we have two independent normal variables, x and y, and they have the constants a and p. So if we have x plus minus y, what happens is that it's still a normal distribution, where it's going to be mu times x plus mu times y plus the mu of the sigma of x squared plus sigma of y squared. Then for ax plus b, we apply the a to just the x, then we add a b, and if we have ax plus by, we apply the a to the x stuff, the b to the y stuff. So the mean and variance of the distribution can be shown using the properties also in previous chapters. So everything in this is also associative and commutative. So x plus y, if x plus b, so on and so forth. It's the same as discrete random variables also. And then another example, let x and y be two independent normal random variables. The means of x and y are 10 and 12 respectively, and the standard deviations are 2 and 3 respectively. So find the probability that x plus y is less than or equal to 18, the probability that y is less than x, and probability that 4x plus 5y is greater than 90, stating clearly the means and variances in this case. So we are going to write down what x and y plots are. So x is a normal with 10 and 2 square as the mean and the variance respectively. And then for y, we have 12 and 3 square. So if you want to combine those together, let's put x and y together. So what happens is that we are going to have 10 plus 12, that's the mean. Then we have 2 square plus 3 square, and then square root, and then square again. Basically, what we're doing here is we are going to find the variance. Then we square root together and division square. It's quite confusing, but basically the final variance is 13. Then we want to find the probability that x plus y is less than or equal to 18. We put these new values in the GC because we know the mean and the standard deviation. So we get a 0.134. That's the answer. Then for the probability that y is less than x, it's the same as saying that probability of x minus y is greater than 0. So we're going to have x minus y, we have a normal distribution, and the mean will be 10 minus 12, which is how we get a minus 2. And then our variance is the same as x plus y. So x plus y, x minus y, they're the same variance, which is why you still have it as 13. So to get the probability that y less than x, is basically 1 minus the probability that x minus y is less than 0, which will be 0.290. Then lastly, for 4x plus 5y, we're going to have a mean which is 4 times of the 10 plus 5 times of 12, that's 100. And then if you do the calculation as well, you get the standard deviation of 17. So the variance is 17 squared. Find the probability, put it into the GC, you get 0.722 also. So another thing to look out for is the difference between x1 plus x2 and the random variable of 2x. So if we let x be the normal with mean mu and variance sigma squared, we write x1 and x2 to denote two independent and identically distributed observation of x. So let's say for instance, if x denotes the height of a year 6 male student, and x1 denotes the height of a male student in class A, and x2 denotes the height of a male in class B, we write 2x to denote twice the value of one observation of x. So x1 plus x2 is two different people. 2x is twice of one person. So the difference is that if you want to find a mean, it's going to be the expectation of x1 plus the expectation of x2 is 2 mu. Likewise for expectation of 2x, it's going to be 2 mu as well. But the difference is that for the variance, when we find variance of x1 plus x2, it's just summation of the two variants. But when we have variance of 2x, that 2, we're going to square it. So what happens is that we get 4 sigma squared as compared to 2 sigma squared in x1 plus x2. So this is the difference between x1 and x2. You cannot, for example, just have replace your x1 plus x2 as 2x, because actually there is a difference between the two of them. So for example, we have a factory producing sweets, such that the mass of a packet of sweets is normally distributed with mean 60 and standard deviation 7. So find the probability that if 3 sweet packets are chosen at random, the probability that the total mass exceeds 160. Then another question is, if one packet of sweet is chosen, find the probability that is 3 times of its mass will exceed 160 grams. So the first part is y equal x1 plus x2 plus x3. We will get a variance of 147. And then our mean will still be 180. So using GC, you get 0.950. But if we try t equal 3x, what happens is that instead of 3 times 7 squared, we get 3 squared times 7 squared, so 21 squared. That's a lot greater than 147. And we punch it into the GC, we actually get a smaller probability. So that is the difference between this. Even though we have technically 3, they are different from each other. And then another example. So the height of a randomly chosen male student from a population may be assumed to have a normal distribution with mean 1.60 meters and standard deviation 0.2 meters. So 2 male students are randomly chosen, and then we want to find a probability that their total height exceeds 3.4 meters, and then their heights differ from each other by less than 0.1 meters. So let's let x be the height of a randomly chosen male student in meters. So 1.60 and 0.2 squared. So we let x1 and x2 be the heights of two randomly chosen male students. So we want to find the expected value and the variance. So ex1 plus x2 is basically the sum of 1.6 plus 1.6. You get your 3.2. And the variance of x1 plus x2 is just the sum of two variances. So in this case, 0.2 squared plus 0.2 squared equals 0.08. So therefore, x1 plus x2 is normal with mean 3.2 and variance 0.08. Then we put into the GC, we get a probability of 0.240. Then for the second part, will the x be the height of a randomly chosen male student in meters, where x has a normal distribution of mean 1.6 and then the standard deviation is 0.2 squared. So we want to find the expected value of x1 minus x2, which is basically 1.6 minus 1.6 equals 0. But then for the variance, it's going to be x1 plus x2, which will lead to 0.08 also. So if you want the heights to differ by less than 0.1, it's the same as saying the modulus of x1 minus x2 is less than 0.1. Or in other words, finding a probability that 0.1 is less than x1, which is less than 0.1. And if we put it into the GC, you get a final answer of 0.276. Then yeah, the last part. 10 male students are randomly selected from a population. Let x bar be the average height of these 10 students. Find the expectation and variance of x bar, and hence take the distribution. So we'll let x be the height of a randomly chosen male student in meters. So 1.6 and 0.2 square here. Here we have x bar. We're going to take the expected value of 10 students and then divide by 10. So 1 over 10 times these 10 expectations, which will still lead to 1.6. Because we're basically taking divide by 10 of 10 students. So 10 over 10, 1. Then for the variance, it's just going to be the variance of all these x1 to x10 divided by 10. The thing is that because you have the 1 over 10 and it's a multiplier, what happens is that you have a 1 over 10 all square times the variance of this. So what happens is that 1 over 100 times these 10 variances. So 1 over 100 times 10 times the 0.2 we have, we'll get a 0.004. So finally, our distribution is going to be x bar has a normal distribution of 1.6 and then the variance is 0.004 respectively. So now to the question, then there are mainly 6 questions I want to go through. Yeah. So the first part is that given that x has the normal distribution of 85 and 34, find the value of k or the range of values of k were appropriate such that probability of k less than x less than 90 equals 0.1 and the probability that x is less than k is greater than 0.2. So what we're looking at here is that we're going to use the difference between two lactales. So we're going to look at probability that x is less than 90 minus the probability that x is less than k. Because probability that x is less than 90, it also includes anything less than k. So what we want to do is we want to find this intersection. So let's say along a distribution curve, our 90 is here, our k is here. If we find everything less than k, it will be from here. But less than 90, it will be everything here. So there's like a middle point here, and that's the in-between range we're finding. So we do that, and then given that we have the known values of the mean and mu, the mean and sigma, we can then put it into the GC. And so the probability that x less than k is just going to be 0.8041 minus 0.1 equals 0.704. And then for part 2, find the probability that x is less than k is greater than 0.2. We're going to consider that this probability is actually 0.2. So from our GC, we know that our k should be equal to 80.1 if we get this specific value. But if we want our k to be such that this probability is more than 0.2, we're going to look at it such that k is greater than 80.1. So you just consider like where the 80.1 lies on the spectrum. So for example, if our k is greater than 80.1, then that means we are looking at a further value. So that's why we are considering k more than 80.1. Whereas if k is like less than 81, like 79, there's still more area after like the part of the graph. And so in that case, it will be less than 0.2. And so that's why in this case, we have k more than 80.1. The mass of a chocolate bar is normally distributed with mean 45 grams and standard deviation 1.5951. The mass of a bar of candy is normally distributed with mean 90 grams and standard deviation 10 grams. Given that the probability that the total mass of all randomly chosen bars of chocolate is within m grams or twice the mass of a randomly chosen candy bar is more than 0.13, find the range of values for m, and this is worth 4 marks. So first thing first, we lay down all the information about x and y. So with that be the weather variable denoting the mass of a chocolate bar and candy bar respectively. And so that's the information we lay down. Then you want to find x1 plus x2 plus x3 plus x4 minus 2y. So we are going to do that. So the mean will be 4 times of 45 minus 2 times of 90. And then the new variance will be 4 times 1.5951 square plus 2 square times 10 square. So this will lead to a new mean of 0 and variance of 410. So we want to find the probability that the mean, no, x1 plus x2 plus x3 plus x4 minus 2y, that modulus less than m is greater than 0.13. So the thing is that what this finds is like a middle range. So there's the left tail, the right tail, and then this middle part, which is the where the modulus and a given probability lies. So what we're going to do is we're going to look at the left tail exactly. We're going to take 1 minus this 0.13 in the middle, divide by 2, and you just get this left tail on the side. So in that case, we can then have a way to find out m. Because of the symmetry, we can divide by 2. So after this, we can then inverse norm. So it will be 0.87 divided by 2, 0.435. We're going to inverse norm 0.435, and by right, we will be able to get the m being greater than 3.32. Then for the next question, with the move towards automated services at a bank, only 2 cashiers will be deployed to serve customers wanting to withdraw or deposit cash. For each cashier, the bank is observed that the time taken to service a customer is a random variable having a distribution with mean 150 seconds and standard deviation 45 seconds. So find the probability that the time taken for a randomly chosen customer to be served by a cashier is more than 180. So this part is quite simple. Just let x be the amount of time taken for a randomly chosen customer to be served by the cashier. So we lay down the information. X is a normal with mean 150 and variance 45 squared. So just put it into a GC, the probability that is greater than 180 will just be 0.252. Then for part 2, one of the 2 cashiers serve 2 customers, one straight after the other. By stating a necessary assumption, find the probability that the total time taken by the cashier is less than 200 seconds. So this is where we talk about assumptions. So whenever we have assumptions, the assumption will be that the first variable, like the first measurement, is independent of the second measurement. So in this case, we need to conceptualize it to the question. So the time taken to serve a customer is independent of the time taken to serve other customers by the same cashier. So that's usually the assumption we make. Whether or not is another context, it will always be something related to the independence. So the expected value of x1 plus x2 is just 2ex. So 2150, which is 300. Then the variance will just be 2 of the variance per x, which is how you get 4050. So x1 plus x2 is just going to be a normal distribution function with mean 300 and standard deviation square root of 4050. Then if you want to find a probability that is less than 200, we just put it into the GC. We should be able to get 0.0581. Then for the next question, this is about the standardization again because we have unknown mu here. So basically this hair salon offers hair styling services. Then the time spent by male and female customers is denoted by M and F respectively, which both follow independent normal distribution. So given that M is less than 32 equals M is greater than 67, we are going to state the value of mu. Then find the probability that the average time spent by 5 randomly chosen females is more than 3 times the time spent by randomly chosen male customer. State clearly the mean and variance of any normal distribution used in your calculation. Then the last part is the commenting on whether the times are representing by appropriate model. So for the first part, we want to find the mu value. So basically, because they already say that one left tail is equal to the right tail, they are basically there and equal to each other because of symmetry. So how we find the mu is just going to be 32 plus 67 divided by 2. That will give us a 49.5, which gives us the middle value, which is our mu. Then we're going to lay out the information for M and female. So M will be mean of 49.5 and then standard deviation 18. Then females will be a mean of 71 and then the variance is 35 squared. So what is going to happen is that we're going to find the probability that 5 probability that the average time spent by 5 females is more than 3 times spent by a randomly chosen male customer. So basically I created f prime, which in other words is just 71 still, but then our variance we divide by 5 because we have the average. So that's how we take it divided by 5. So our new variable for f is still going to be 71 because the average of 5 is the same as the average of 1, so it's still 71. Then we have the 35 squared divided by 5. So the expected value in this case will be just our 71 minus 3 expected value of males. So minus 3 of 49.5 minus 77.5 And the variance will be variance of f prime plus 3 square of the variance of n. So 245 plus 3 times 18 square, 3161. So the required probability is that f prime is greater than 3m. If we bring that over to the left hand side, it's a probability that f prime minus 3m greater than 0, which if we put our GC will be 0.0840. Then for the last part, how you want to decide whether this is a appropriate model or not? For any question, to solve this part, is basically going to find a probability that something is less than 0. So the thing is that when we put into the GC, we find that actually in this case it's 0.0213, which is about 2%. It's still a significant probability. But the thing is that obviously we cannot spend negative time in the salon. So in that case, this is how we debate that this is an unrealistic model. Then the next question. So a popular brand of toothpaste is holding a win as you eat promotion. So 2% of analyzed packets produced during the promotional period contain price winning coupons, with each packet containing at most one price winning coupon. So they are each sold in a family pack containing 10 randomly chosen size pack. So this is kind of like a probability and binomial question also. But first, find the probability that a randomly chosen family pack contains no winning coupon. Then part 2, the family packs are delivered to supermarkets in cartons. Each carton contains 20 family packs. Find the probability that the chosen carton contains more than 16 family packs with no winning coupon. So these first two parts are interrelated to each other, but we will solve part 1 first. So we let X be the number of packets of toothpaste with winning coupon in a family pack. So each packet has 10. So that's our sample size. Then the probability that it has the coupon is 0.02. So if you want it to have no winning coupon, it is going to be probability that X equals 0, 0.817. Then we create our new variable for part 2. That Y be the number of family packs with no winning coupon. So we already found the probability that a family packet has no winning coupon. In that case, it's 0.817. So that's our probability. I have a sample size of 20. If I want to find a probability that we have more than 16. So we'll do the complement. 1 minus anything that's equal to 16 or less. That's how we get our 0.489. Then next part, we want to find a particular family buying one family pack every week. For 5 consecutive weeks, find the probability that the 5th week is the second week that the family does not get any winning coupon. So basically what this means is that we want to have one winning week. And then after that, nothing. Until the 5th week is when we get our second. So yeah, we let W be the number of weeks that the family does not get any winning coupon in 4 weeks. So our sample size will be 4 and probably 0.17. So what happens is that we will have one winning phase. So what the PW1 equals is that we get only one winning ticket in 4 weeks. Then we multiply by the 0.817 to represent the 5th week. And so that's how we get our final answer, which is 0.0163. Yeah. Then for the last part, part 4, an event organizer stocks out 1,000 standard size packets per event. The probability of having at least K winning coupons is more than 0.15. Using a suitable approximation, find the largest possible value of K. So in this case, this is where our normal distribution comes into play. Because what happens is that whenever your N is more than 2025, or like 2025, around there, you can actually use a central limit theorem. So what central limit theorem is that when the sample size N is very large, we can approximate our random variable using normal distribution. And this is something that you'll use quite a lot. So we're going to let T be the number of packets of toothpaste with winning coupons out of 1,000 ticks. So the probability is going to be 0.02. We're not looking at a family pack anymore. We're looking specifically at these standard size packs. So after that, and you have to write this, since n equal 1,000 is large, by central limit theorem, we can approximate T using a normal distribution. So the expected value will just be NP. So 1,000 times 0.02 equal 20. Then the variance is NP times 1 minus T, and we get 19.6. So that's our new variable. 20, and then 19.6 as the mean and the variance respectively. Then using our GC, we're going to key in the values, and then we'll do some observation. And eventually you'll find that the largest possible value of K is 25. Then for the last question, the height XTM or boys in a school may be assumed to follow a random distribution with mean mu and variance sigma square. So given that x less than 1.5 equal x greater than 1.5 equal 0.025, we can find the value of mu and sigma square. Then hence find the probability that the total height of 2 randomly chosen boys exceed 2 times the height of a third randomly chosen boy by at least 5 cm. Part 2, the mean height of 50 randomly chosen boys is less than 172 cm. So you want to find the probability of that. Then for part B, the mass of a randomly chosen box of hamster food has mean μ and standard deviation 5 gram. So a large number of boxes is taken. Find the least value of n such that probability of x bar minus mu less than 1 is greater than 0.99, where x bar is the sample mean. So we look at the first part first, finding the mu and the sigma square. So like in the previous part, because x is less than 155, it's the same as x greater than 155. We use symmetry to find that the mu is 170. Then we're going to look at our x less than 155, which is having a probability of 0.025. So we're going to standardize it. 155 minus our 170 divided by sigma will still equal to 0.025. Use GC to inverse norm. You'll find out that the expression 155 minus 170 over sigma is minus 1.96. Solve for sigma square, you get 58.6. Then, for part 1, we have the random variable x is a normal distribution with mean 170 and then the variance mean 7.65 square. So if you want to find the expected value of 2 boys minus 2 times the height of a third boy, it's going to be x plus ex minus 2ex equals 0. Then the variance will just be x1 plus x2 minus 2 times of x3. So the variance overall is 1 variance plus another variance plus 2 squared of a variance equals 6 variance, which in this case equals 351.42. So our new variable for part 1 will have a normal with mean 0 and 351.42 as our variance. So then we find the probability that is more than or equal to 5, and that will give us 0.394. Then for the last part, we'll have x bar having a normal of 170 and then 7.6531 squared over 50. We're going to find the probability that of this 50 is less than 172, which will equal to 0.968. This is a bit on our sampling and hypo-testing chapter as well, but basically if you want to find the mean height of randomly chosen boys, you are always going to divide by the sample size to get the variance. The mean remains the same, but the variance you have to divide by whatever is the sample size. So after you do that, you can get your 0.968. Sorry for the confusion. So yeah, then for the last part, we are gonna get our p x bar minus mu less than 1 greater than 0.99, and then we want to find the value of n. So what happens is that we're going to standardize the entire thing. So we can replace our sigma with 5 squared, and then we simplify the entire thing. It will end up being modulus x less than square root n over 5. Then to remove the modulus, it's basically the in-between of minus square root n over 5 and the positive of square root n over 5 greater than 0.99. So what happens is that now we're going to look into the GC. We're going to put our lower and upper limits as such, our mu as 0 and sigma as 1, because we already standardized the whole thing. And then we'll put it into the GC, and then we're going to find that actually the least value of n is 166. So that's how we solve that part. I'm not sure why the question talked about hamster food, but this is the correct question. So that's all I have for this question. Hopefully you learned something interesting, and if not, hope to see you in the next video. If you have any questions, you can always find me on Telegram as well. Alright.